So this is our part two of our circular functions, graphs, and properties. And we don't have a whole lot to do in this section or the rest of the section. What we just have to figure out is we keep calling these trig things, we keep calling them functions. And so a lot of times if we have something that's a function, we can find the graph of it on the Cartesian coordinate plane. And that's what we're going to look at now is what is the graph if we were to take inputs and into sine or cosine and take their outputs and put it as an ordered pair on our Cartesian coordinate system, our XY plane, what would this look like? So that's what we're going to kind of try and figure out today and get an idea of what these graphs look like. So remember, let me get rid of some of this stuff here. We kind of ended the last lecture with this idea of the unit circle. And so let's kind of go on that and see, oh guys, this is not going to be a circle. Sorry about that. But we found some interesting stuff, right? We found, that if we take 30, 45, and 60, so if we take 30 degrees, this was root 3 over 2 comma 1/2, right? This one was root 2 over 2. If I created a, triangle there, then that would be my x and my y. This one is 1/2 comma root 3 over 2. Okay, this point right here is 1, 0. This guy, we have 0, 1. Again, I'm not going to require you to know the unit circle, but if that is a way that you like to remember the exact values for sine, cosine, and tangent of 30, 45, and 60, do it. And I should really be saying pi over 6, pi over 4, and pi over 3. Right, then go for it. So this is totally up to you if you want to do that. If I grab these values over here, we just know this is a reflection. So like this point right here would just be the opposite x value because I'm in the second quadrant and I should have negative x's. This one, then all of these would be basically the same points in the first quadrant except the x values are going to be negative. 1/2 root 3 over 2. Right, and then that point right there is a negative 1, 0. And we could go around and we could do that for, oh man, I'm really messing up my circle, for all of these points that have a reference angle of either 30, 45, or 60 degrees. So, and of course, what do we know now then? We know that if I take the sine of some real number now, I know we're going to keep thinking of it as angles, but some real number s, that's just going to be my y coordinate. Cosine of s is just going to be my x coordinate, and tangent of s is a y over x. And then don't forget cosecant of s is 1 over y. Secant of s will be 1 over x. And then we have cotangent of s is x over y. Okay, so what I want to look at is the graph of, figure out kind of, if I took these values, right, if I inputted the s's and I graphed that along my horizontal axis, and then I graphed the outputs along my vertical axis, what will happen? So let's look first at y equals the sine of s. So if you thought I couldn't draw, which I'm sure you thought this, I couldn't draw a circle, just let's see what's happening here. Okay, so sine of s, so I'm gonna look at some of my inputs here. Let's just kind of start with pi over 2. We'll do pi right here, 3 pi over 2, 2 pi, and then we could go, more than that. We could do 5 pi over 2, and keep going. And then of course, could we consider negative angles? Sure we can, because negative angles just go the opposite direction, right? We can really consider any real number. That's kind of the gist of this whole section, which is pretty powerful, is that we can really consider any real number that sine and cosine can do that. And I apologize if those aren't perfectly, oh well. Oh well. All right, so let's see what's going to happen here. So if you notice all of these values are going to be between -1 and 1. And why do we get that? Because remember, we're just taking ratios of sides of triangles with the hypotenuse always on the bottom. So remember, the hypotenuse of a triangle is always the longest side of the triangle. And if that's the denominator, we're never getting a number bigger than 1, because a number bigger than 1 means the numerator is bigger than the denominator. That's my calculator, and I just threw on the floor. That's good for it. Show it who's boss every once in a while. All right. So let's do this. So at 0, let's plug in some points here. So when S, so remember this is my S and this is my sine of S. So when S is 0, what is sine? Well, it's the y value, so it's actually going to go through the origin here. Let's look at, pi over 4, or actually, let's go ahead. This one's going to be kind of nice. Let's look at 30 degrees. So 30 degrees is about a third of pi over 2. I'm going to kind of mark these 3 little spots. That'll be my 30, 45, and 60. And then let's go ahead and get a 1. So if pi over 2 is like 1.5, I can tell you that more. 1.57. So when I go to make these, I'm going to make, this isn't going to be perfect, but I'm going to make this distance relatively the same as that pi over 2, maybe a little bit shorter. It should be a little bit shorter. But let's see what's going to happen here. So at 30 degrees, sine is 1/2. So at 30 degrees, I'm going to come over here and put 1/2. At 45 degrees, sine is root 2 over 2. So the square root of 2 over 2, whoa, Sarah, what are you doing there? Is about 0.7. So at 45, I'm going to be a little bit closer to 1.7. And then root 3 over 2, if you find that, come on, Sarah, root 3. I know what it is. I think it's 0.86. Ooh, apparently, I don't know how to use a calculator. Does that worry you? It might. 0.866, yes, right. So even closer to 1 at 60 degrees, or at pi over 3, that's what that is. And then at pi over 2, we know we're at 1, right? So we're up here at 1. There is my y coordinate. And then look at what happens over here. So when I go to this next value right here, which this is 120 degrees, the reference angle here, okay, is pi over 3. That's what that reference angle is. So I know that that's kind of the next little step after pi over 2 that I know. And my y coordinate here is root 3 over 2. So it's going to be this little point right here, just kind of reflected over here. At this point right here, which would be this guy right there, I'm pi over 4 away. And again, I'm in the second quadrant, and so I'm about 0.7. Okay, and then at 30 degrees, close to my pi, I'm at 1/2, so I'm going to be kind of the same as this guy here. And then at pi, I'm at 0. So what this does is that this lovely little kind of hump right there. And then you guys notice what's going to happen when we start coming over here, right? And I grab these values right here. When I know that this point right here, right, is just going to be a reflection of this point right here. So the y is going to be negative. So again, I'm 1/2, or I'm 30 degrees, or pi over 6 degrees away from pi. And so I'm just going to have the same values as 30 degrees, except I'm in the third quadrant, so they're all going to be negative. And so we could do that with all of these, right? They're all going to be negative in the third quadrant. Okay, so when I go to graph that, I know then like halfway through I'm going to be at 1/2, and I'm going to be a little bit smaller than that here, and then I'm getting a bit closer to -1, and then sure enough, right at 3 pi over 2, right, what do I have right here? This is not a great graph, but this is 0, -1, and what's my y coordinate there? It's -1. So I get something that goes like this, and then it's going to repeat that right here and come back up to 0. How do I know it's 0 then at 2 pi? Because this is 0 and 2 pi. That's the same, right? So it must be 0. Isn't that great? And then once I get past 2 pi, right, I'm just adding these same angles right here to 2 pi. So I'm going to be getting those same y values, if you notice. I'm going to be getting those same y values. So again, I'm going to, at 5 pi over 2, which is coterminal with pi over 2, I'm going to be up at 1. So these values are going to go up to 1, and then they're going to come back down again at 3 pi and go down. Okay, so when you hear your friends, right, at the party you're at, oh, everyone's talking about it. When you've heard about like the sine wave or the cosine wave, that's what we mean here. It makes like a wave pattern. these trig functions are really useful because they, and I think I told you guys this, like they are really good at modeling things that have any sort of oscillation in them or any repetition in that sense. So like in differential equations a lot, we will talk about mass attached to a spring and how we can, if you pull that spring and let it go, it kind of does this wave pattern. And in differential equations, we find that sine and cosine are involved when we talk about the position function of that. Okay, so let's see what's going to happen over here. So remember, I can put in any real number. I've done that with positive values right now. Let's look at what happens with negative values. So I need to fill in my fourth quadrant here. I'm going to fill this in. This is not the most perfect. This is 30 degrees or pi over 6 degrees away. So I know that this is going to be root 3 over 2. I know x is positive in the fourth quadrant, so this will be a negative 1/2. This is root 2 over 2 and a negative root 2 over 2. Again, because I'm in the fourth quadrant, I know that my y values are going to be the ones that are negative. And then this one right here will be 1/2. Negative root 3 over 2, and then that point right there that I erased is 0, negative 1. Okay, so there's my unit circle, and let's see what happens when we talk about a negative pi over 2. So does that negative pi over 2 make sense in the situation that we're at, right? I'm trying to figure out what happens to sine when I plug in values for s and what does it spit out. Remember, a negative angle just means that I'm going the opposite direction. So like right here, this would be a negative pi over 4, and a negative pi over 4 is just going to be this angle right here. And notice I have that negative root 2 over 2, which is about 0.7. So it's a negative root 2 over 2, so it's about 0.7, right? At 30 degrees, I'm going to be at a negative 1/2. At 60 degrees, I'm at like 0.8. And then at a negative pi over 2, negative pi over 2 is this angle right here. That angle is coterminal with 3 pi over 2, right? So we're going to have the same value right there. Oh, whoops, I didn't keep my yellow. So what is my y value right there? It's a negative 1. So at a negative pi over 2, I'm at a negative 1. And then as you've kind of seen, right, this stuff is just going to kind of start coming back up, just like before. Okay, and negative pi, why is it 0? Because again, if we go negative pi, that's coterminal with pi, and the y coordinate there is 0. Okay, negative 3 pi over 2, we'll just jump up there because we know what's kind of happening. Negative 3 pi over 2 would be this guy, so it's coterminal with pi over 2, and sine at pi over 2 is 1, so sine at negative 3 pi over 2 is going to be 1. And then at a negative 2 pi, we're going to be back at 0. A lot of times, once you know kind of what the graph of this looks like, I'm going to show you this on Desmos so you actually know what it looks like. Once you kind of know what the graph of this looks like, you are going to have to graph this without a calculator. So once you know kind of that it's a wave, what I usually do when I graph this is I graph my x-intercepts and I graph where I know the function is 1 and negative 1. So I know those are always going to occur on the on the axes, right? So I'll put in, what 0 is. I'll put pi over 2, I'll put pi, 3 pi over 2, 2 pi, 5 pi over 2. Here are some things that I need to see. I need to see the sky being a nice, gentle curve, right? It needs to be curvy. So I've had students before, when they graph this, they'll get, the 0 and 1, and they'll connect it all with lines, and they'll say there's the graph of sine. That's not what it looks like. They are not lines. So I don't want to see peaks in terms of like mountain peaks. I want to see nice rolling hills. Okay. And it's not gonna have to be perfect because clearly mine is not, but I need to see some of those things, right? I need to see the behavior of sine of x. And if we look at the graph of sine of x, so if you do Desmos, or if you are going to put this into your calculator, here are a couple of hints. So first of all, when you put this into your calculator, which I'm sorry, I'm recording this at home and I don't have my calculator with me, make sure your mode is in radians, okay? And then when you go, if you do your zoom window, they have a trig option, so you could do zoom trig. Or if you go in, if you notice right here what I'm putting my step to be pi over 2. We could even, put it to be like pi over 4 if we wanted to, or something like that, whatever we want to do there. I think I'll stick with pi over 2 because I think I messed with that and it looks a little bit better. And then remember, the biggest we're going to get on the y-axis for right now is negative 1, or excuse me, the biggest we'll get is 1. The smallest we'll get is negative 1. So you don't have to set your y window to be super tall, because you are just going to be having those values. If you need help with that with the calculator, let me know. I can record you a little video if you'd like on how to put this in your calculator. I apologize I didn't bring that. But let's go ahead and plug this into Desmos. Now I'm going to do y equals sine of x because this is a function and the graph is considering the x-axis and the y-axis, right? Not in terms of an x-coordinate and a y-coordinate. That's what's kind of hard. So remember down here, this was my x and my y-coordinate. That's why your graph uses, or your book uses s instead of x and y, because we don't want you to get confused. Wow, that circle's really bad. Let me look at it from far away. I'm so sorry. They don't want you to get confused there. So let's look back at this. This is a beautiful picture of sine. Again, it's the wave. Notice a couple things about sine. It does go through the origin. The maximum height it gets is -1, right, in the positive direction. The lowest value it takes is, +1. The lowest value it takes is -1. And it has this nice wave pattern. Notice these aren't straight lines, right? It's a nice wave. Okay, let's look at cosine. So this guy you'll need to know how to graph from memory without the use of a calculator. Sorry about that. I know I'm just mean by nature because I'm a math teacher, right? We're just mean by nature. But when you get to calculus or something and we start talking about maybe derivatives of sine and cosine, or we start really working with these functions, it's really important that you kind of remember what, go away. It's important that you know what these graphs look like so you don't have to every time like go through and figure out what they are. I want you to know the graphs of sine, cosine, and tangent and their reciprocal functions because we want to know when we're dealing with this graphs like, okay, well, what's the maximum value of this? We're going to shift these around. We're going to translate them. And so it's going to be important that we know how to do that. So let's figure out cosine here. We won't spend quite as much time on kind of developing the idea of it because we're already at 16 minutes. Oh man, that was horrible. There is a way in Smooth Draw for me to graph straight lines. But clearly I'm not motivated enough to figure that out. All right, we'll try and get these somewhat, they're not that same, but pi over 2, pi, 3 pi over 2, 2 pi. After 2 pi, it starts repeating itself, just like sine. Negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. All right, so let's look at cosine. So cosine, first of all, good old cosine. I like cosine because it just like starts off on a high note. So cosine at 0 degrees or 0 radians, right? What we are looking at, we are going to be looking at x values. So at 0 degrees, what is my x value? Or at 0 radians, it's 0. Or excuse me, it's 1. That's my x value. Then remember, we're taking our x values here. So what cosine does is it gets closer to 1 right away. So at 30 degrees, it's at that 0.86, right? At 45 degrees, it's going to be at half. And then we're just kind of getting lower there. I need to probably bring that up a little bit. Okay, so I'm going to have this kind of thing right here. And then at pi over 2, what is my x value at pi over 2? It's 0, right? Then notice, so I want to point out something too that I didn't point out on sine. This right here from 0 to pi over 2 is quadrant 1. Pi over 2 to pi represents quadrant 2. Pi to pi over 3, right, represents quadrant 3, and this represents quadrant 4. So these intervals right here correspond to my 4 quadrants, and I should have said that with sine. So at pi over 2, I'm at 0. At pi, I'm at -1, right? So I'm going to come down here to -1. Then at 3 pi over 2, I'm back up at 0. And then at 2 pi, which is 0 degrees, I'm back up at 1. So you see cosine also gets this wave-looking function, and it's going to come down like that. And I apologize for the shakiness. Okay, so again, cosine gets this wave-looking function. Look at why this makes sense. Remember, we know cosine is positive in the first and the fourth quadrant, okay? First and fourth quadrant is where cosine is positive because that's where the x values are positive. If you notice here, where is this guy above the x-axis? It's above the x-axis here, and it's above the x-axis here. So look at it is positive in quadrant 1 and quadrant 4, which is what we know about cosine to be true. Its graph should, verify those things that we know to be true. All right, let's go the opposite direction. If we go in negative pi over 2, so that's going to be going this way, right? Negative pi over 2. What is the cosine of a negative pi over 2? It's going to be 0. And actually, the cool thing about cosine, which we're going to talk about, is it's what we call an even function. It has this symmetry about the y-axis, meaning if you put in, pi over 4, you're going to get the same thing as a negative pi over 4 because cosine is positive in 1 and 4. Then at negative pi, which is all the way around, we're going to get negative 1. Negative 3 pi over 2, we get 0. And negative 2 pi, which means we've just gone all the way around, we're back to 1. And then again, you get the same kind of cyclic nature here. Let me graph this on Desmos for you. So cosine, if you notice, starts up on the y-axis at 1, whereas sine went through the origin, but it still has that nice wave looking. Oh, this is not a great graph. I never tell you when you study mathematics that you're going to have to be somewhat of an artist as well. So let's put in cosine of x. So just what we had found, right? It's going to be positive. Positive, when we're here on the first quadrant, or this right here is this fourth quadrant. Okay, negative on the second and third quadrant, and so on and so forth. Okay, so there's cosine. All right, so let's develop the other function. So, and I should have put there. Well, now I'm going to just get rid of it, but that was cosine of s. Okay, so let's see what about tangent. Okay, so tangent, we're going to kind of do the same thing. I'm just going to see kind of what the behavior of this graph looks like. I know this is taking us a while to go through this, but this is important. It's important to know what the graphs of these functions look like. We're going to use them quite a bit from now on. Tangent's an interesting one. I think you're going to find what makes it interesting is that we have a fraction, right? And so anytime you get a fraction, we're going to have maybe some oddball behavior wherever the denominator is 0. So let's kind of start with the same idea here, and let's just start at 0 and work our way through it. So we're going to do tangent of s. And remember, tangent is going to be y over x, sine over cosine, which we'll talk about later. So y over x. Okay, so let's start at 0 degrees. If I take y, 0 divided by 1, right, I get 0. Okay. This one's a little bit harder to do, but if I took y divided by x, I would get 1 over root 3. Okay, and then here, let's go to this one because this is going to be easier. Root 2 divided by root 2 is 1, right? I'm at 1. And now, okay, so let's look at this next value here. I'm going to get root 3 over 2 over 1/2. So the tangent of that is just going to be root 3. So if you notice, let's do the square root of 3 here. That is about 1.73. So at 60 degrees, I'm already bigger than 1. I'm going to be up here at like 1.73. Let's get a little closer. I'm going to use my calculator here, and I'm going to take the tangent of, let me see what mode I'm in. Okay, I'm going to take the tangent of something really close to pi over 2. And for sake of brevity, I'm going to just go ahead and think about this in degrees. So I know pi over 2 is 90 degrees. I'm going to take the tangent of 70 degrees. So the tangent of 70 degrees is 2.75. Let's take the tangent of 80 degrees. Wow, that's already 5.67. Let's take the tangent of 88 degrees. Oh man, we're already at 28.64. If I take the tangent of 89 degrees, I'm at 57. If I take the tangent of 89.9 degrees, I'm at 89.9. That's weird. Oh no, I forgot to put the tangent in there. Yeah, tangent of 89.9 degrees is 572. So guys, here's what's going on. If I actually tried to put in pi over 2, notice what I would have. I would have 1 divided by 0, which clearly we cannot have. So what we end up having at pi over 2 is something called a vertical asymptote. Right? We've talked about those before. And as we get closer and closer to pi over 2, these numbers are getting really, 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 really large. So we're going to have something, whoa, You're not supposed to cross vertical asymptotes. You can cross horizontal, but vertical, you may not. So this is what happens as we get closer to pi over 2. Our y values are going to get bigger than our x values because, as you can see, my x values are going to 0, but my y values are going to 1. So I'm basically taking, y values and then dividing them by really, 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 really small x values, which in turn actually gives me really, really big ones. Now, the minute I get past pi over 2, let's just jump to pi really quick. If I did pi, 0 divided by -1 is just going to be 0. But let's take some values of tangent that are close to 90 but on the other side. So tangent of 90.1 is a -572. Tangent of 90.5, we'll get a little bit away from it, is a -114. So what actually happens is, as you approach pi over 2 from the right, you're getting down to really, really, really large negative numbers. And then I'm just going to break the suspense here and tell you that at 3 pi over 2, where my x value is 0 again, we're just going to have kind of the same behavior. So I'm going to go negative when I approach it from the right, but when I approach this 3 pi over 2 from the left, we're going to positive infinity. Same thing here at 2 pi m at 0. I'm just going to start down here and come up here, and at 5 pi over 2, I'm going to have a dotted line. Okay, so this guy actually is kind of the same behavior as in between these pi over 2's. Okay, at negative pi, it's at 0. Now, I don't want to say it's a multiple of pi over 2. That's not true, because pi is a multiple of pi over 2, right? I just multiply it by 2. But what it is it's basically pi over 2 plus or minus any multiple of pi, because this distance, as you see right here, is pi. Okay, man, I'm at 26 minutes already. Goodness. So this is my tangent. Let me kind of show you tangent on decimals. Tangent's a little funky. We have vertical asymptotes at pi over 2, and then any multiple of pi plus pi over 2. But if I graph this, we get tangent of x. Now, your calculator, if you graph this on your calculator, might put a line right here on the pi over 2 because it doesn't realize there's an asymptote there, and it's trying to connect those two dots because it obviously can't make it go to infinity. But this is what tangent looks like. I can zoom out and you can see we have an infinite number of vertical asymptotes. Okay, so let's write down a couple of things about these functions, sine, cosine, and tangent. And then what I would like to do is I would actually, let's see here. I want to wait on graphing. No, we'll do cosecant and secant. And I'm just going to kind of show you those. I hope you'll be all right with that, and you'll just have to kind of believe me. But I do want you to know those functions as well. So let's write down kind of some properties about this. Okay, so some properties of these graphs. We'll just say properties of sine, cosine, and tangent graphs. Okay, so first of all, let's talk about sine of x. So the sine of x, and I'm just putting x instead of s, the domain, okay, is everything. We can put in anything we want. And the range, what are the y values that we're going to go between? We're going to go between -1 and 1. Same thing with cosine of x. Its domain is -infinity to infinity, and its range is -1 to 1. Okay, and then tangent of x, this guy's a little bit weird. So tangent of x, its domain, and I'm going to write this a little bit strange, is all x as long as x is not equal to pi over 2 plus any multiple of pi. So I'm going to say k pi for k, an integer. So what this is saying is all my x's are invited. We've done set notation before. All my x's are invited to the party as long as x is not either pi over 2 or any distance that is pi away from pi over 2. Because what that's going to give me is it's going to give me a point on the x or the y-axis. Tangent can't handle that, you guys. The range, as you see, is -infinity to infinity. Okay. A couple things about sine. This guy goes through the origin, so sometimes I'll just put like, okay, I know sine goes through 0, 0. Cosine has a y-intercept of 0, 1. It kind of starts up at that one spot for the y-intercept. And those are our graphs. Those are our three main graphs of sine, cosine, and tangent. A couple other things about these guys. Sine of x is what we say is an odd function. And here's what we know about an odd function. So in the case of sine, when I take the sine of negative x, that is the same thing as making my y values negative. So like if I have the sine of pi over 3, and then if I take the sine of a negative pi over 3, that is going to be the same as a negative of the sine of pi over 3. Basically, if I make my x values negative, then I get that same value, but it's negative y values. The other thing that odd means is that it has symmetry about the origin. So if you reflected about the y-axis and then reflected about the x-axis, you will get the same thing. Cosine is what we call an even function. That means it has symmetry about just the y-axis. If you fold up the y-axis, it'll lie on itself. I'm just going to put symmetry y-axis. And cosine, what that means to be an even function is, if I take the cosine of a negative x or negative s, it just spits out the same thing as if it was positive, okay? So, if you kind of remember with cosine, that was true, right? Cosine kind of did this. So remember, these are all my positive values between 0 and pi over 2. Notice if you take the negative values between 0 and pi over 2, they're exactly the same, right? So I don't have that different sign, S-I-G-N. Whereas if you look at sine, notice if I took these positive values, and then if I took the opposite of them, it actually gives me the negative y values down below. Okay, so those are some interesting things about sine and cosine. Now we're at 31 minutes. Let's chat about the other three functions really quick, and I'm going to just do some pretty simple sketches for you of those. So let's start with y equals cosecant. I'm just going to start using x's now. I hope you don't mind. Cosecant of x. And remember, cosecant, right? I should use s's, but we're going to eventually use x anyway, is 1 over sine. Now, here's what you have to worry about when you're worrying about the reciprocal functions. You have to determine where you have asymptotes, because we have fractions now. So we are going to have asymptotes. Remember, sine are my y values. So we're going to have asymptotes anywhere where we're on the x-axis. So I'm just going to kind of draw my unit circle. So I'm going to have asymptotes. Where am I going to have asymptotes? I'm going to have them at 0, pi, 2 pi, right? 3 pi, dot, dot, dot. So what we say is we're going to have asymptotes at any integer multiple of pi. So when you graph cosecant, what happens then, okay, is that I'm going to have, here's my pi over 2 pi, 3 pi over 2, 2 pi. So here's my pi. I'm going to have an asymptote here because sine of pi is 0. Okay, this is my negative pi. I'm going to have an asymptote here. You actually have an asymptote along the y-axis. And then I'm going to have an asymptote at 2 pi and so on and so forth. Okay, so if I look at this, what happens if you look at the graph of sine and you kind of just invert it, and you can look at your book does a nice picture of it, but if I just kind of invert it, what's the at pi over 2, I'm going to have 1, but then instead of being bounded between -1 and 1, cosecant actually doesn't spit out anything between -1 and 1. That's kind of the funny thing about cosecant. So cosecant, and you can look at if you take cosecant is your hypotenuse divided by your opposite side, right? So it kind of makes sense because my hypotenuse is always bigger than my opposite side. So I'm always going to get a number that's bigger than 1. There's cosecant. So I have these cool little, they're not parabolas, but they kind of look like parabola looking shapes. You should really Google the trigonometric function dances. They're really good. You will love it. Let's look at secant of x. Okay, so secant, where is secant going to have problems, right? So really quick about cosecant, the domain, right, are all x's as long as x does not equal k pi, where k is an integer. It's not a fraction. Can be negative. The range in this case is from -infinity up to -1, union, skip everything in between, and then grab it back at, oh, that's an open, at 1. Okay, good. All right, you guys. Let's look at secant really quick. So secant is, remember, 1 over cosine. So I think I had said at one point that like secant and tangent are kind of friends. The reason that they're kind of friends is they're going to have the same asymptotes. So like when we get to some of our identities, we're going to actually see that that they're kind of friends because they have kind of that same idea. So where are the asymptotes going to occur for cosine? Remember, cosine are your x values. So where is x 0? X is 0 on the y-axis, right? So x, these are going to occur the same thing as tangent, pi, any pi over 2 plus k pi. So add pi over 2, add pi, we have an asymptote. Add another pi, we have an asymptote. Take away a pi, right? Go the opposite direction, there's an asymptote. And so secant's going to be quite similar. We're going to go like this, kind of a lot like cosecant. We're just going to have them kind of shifted over a little bit. So notice secant's going to start, going to be cross the y-axis right at 1. And so my domain here is just like tangent, all x such that x is not equal to pi over 2 plus k pi for k an integer. And then my range is the same thing. Range is -infinity to -1, union 1 to infinity. Okay? Those are pretty tricky. So try those out, look at those. You know, I'm more interested that you know how to graph sine, cosine, and tangent by hand. Cosecant and secant, I'll probably be a little bit more lenient on maybe letting you use a calculator or something to graph those. And same thing with cotangent. So let's look at cotangent. So cotangent is 1 over tangent, right? And remember, tangent were our y over x, so that's like basically x over y, and don't let that confuse you with these x and y's. I should have probably stayed with s's. But where are my asymptotes going to occur for cotangent? They are going to occur on the y, whenever y is 0, which is the x-axis, right? So basically at 0, pi, 2 pi, 3 pi, so basically at any k pi. So we're also going to see that cotangent and cosecant are friends. So pi over 2 pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. And I know at 0 I have an asymptote, at pi I have an asymptote, 2 pi, negative pi, and negative 3 pi. So, okay, so let's think about this. So remember tangent, right, looked like that. So what cotangent is going to do is it's going to look similar to that. It's just going to go the opposite direction. Okay, let me make sure I get this the right way. So cotangent, if you take, when is x 0 and y isn't 0? That's on the y-axis, right? So at pi over 2, it's actually going to be at 0. At 3 pi over 2, it'll be at 0. Negative pi over 2, 0, 0. And then what this guy is going to do is just kind of, at pi over 4, it's 1. So it's going to do kind of the same thing as tangent. It looks a little bit like x cubed. It's not quite as curvy as x cubed. Although x cube's not super curvy, but sometimes we just bring that in for emphasis. But this is what cotangent's going to look like. Very, very similar to tangent. Okay, it's just going to be shifted over because your asymptotes are different and kind of go the different direction. So my domain for this is all x values as long as x is not equal to k pi, where k is a multiple or is an integer. And then my range, of course, for this guy is -infinity to infinity, just like tangent. All right, you guys, so we are about done. The only thing that I want to talk about really quick that I kind of skipped over, sorry, before I talked about came and started talking about the reciprocal function is I just want to give you a definition of what we call a periodic function. Okay, and we're going to talk more about sine and cosine and some properties of the graphs in the next section. But here's what a periodic function is. So a function f is said to be periodic if there exists a positive constant p such that, f of s plus p equals f of s for all s in the domain of f. Okay, now the smallest value p, and this is going to be something we talk about a lot. The smallest value of p is called the period. So we might rewrite that for sine and cosine. That's what we call the period of the function. And sine and cosine are, well, all of these functions are periodic because, right, if I take the sine, I'm going to just do degrees for right now because this is a little bit easier, of 30 degrees and I add 360 to it, you guys, that's exactly the same as the sine of 30 degrees, right? If I add 360 degrees to anything, I'm going to get everything the same back out. So when we look at sine and cosine and cosecant and secant are all periodic functions, and they have a period of 2 pi. Okay, every 2 pi it starts repeating. Interesting thing about tangent and cotangent is that they actually just have a period of pi over 2. If you look at it, go back and look at the graph of tangent, right? It starts repeating itself at every pi over 2. The other thing is if you look at the graphs, so if you look at sine, right, which does something like this, another way to think of the period is that it's the amount of time that it takes, or the distance it takes for it to complete one cycle. And one cycle, what we mean by that is that it's gone through all of the total values in its range, and then it starts repeating it again. So you can see that with cosine also, right? If you look at how long does it take to complete one cycle, I would come back up here. And this point right here would be 2 pi. Whereas tangent, right, does something like this. And then it automatically starts repeating again. And here's negative pi over 2 and pi over 2. And you notice that distance right there is pi. Okay. We have a couple more things to talk about. We need to talk about like amplitude and stuff. I'm just going to tell you right now, we're going to deal with amplitude later, but the amplitude of sine and cosine are 1. So the definition of amplitude is like half the distance between the maximum and minimum value. But you basically, if you could just cut this graph in half, I told you we're going to talk about later, and apparently I'm not going to. If you cut this graph in half, how far above does it go and how far below does it go? So the amplitude, if you get any questions about that on your homework, which maybe you will, is 1. Same thing here if I cut cosine in half, but we're going to talk about this more in the next section. The amplitude of cosine is also 1, and we'll talk about that more in the next section. Whew, guys, 43 minutes. If you're still with me, I am impressed. Practice graphing these functions. Sit down and graph them. Don't just put them into your calculator and be like, oh yeah, I know what it looks like. You're gonna have to graph sine, cosine, and tangent by hand without a calculator. So practice, 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 and please let me know if you have any questions.